Hello everyone. So today we'll discuss a couple of methods for deciding optimal number of clusters. This can work in case of k-medoids algorithm, but not only that, it can work even for k-means or hierarchical algorithms. Okay, so the method has nothing to do with the clustering algorithm. Okay, you might remember we discussed this during multivariate class that there are almost like 30 different methods for deciding optimal number of clusters. Many of them are based on within cluster sum of square, between cluster sum of squares, etc. So we are going to study two methods today. Okay, so let me write down the name of the first method. So the first method is known as gap statistics. Okay, so gap statistic. It was proposed by Tipshirani. Now, how do you compute this gap statistic? So, we want to decide optimal number of clusters. So, let k be the number of clusters with which we have done clustering right now. So, k is number of clusters. Then, what we are going to do? We are going to compute total within cluster sum of squares. Okay. Total within cluster sum of squares. Now, if this is categorical data, then we can't compute sum of squares, right? For continuous data, we can compute sum of squares type of thing. But for categorical data, we can't compute that. However, for categorical data, what we can do is, just like we did in k-medoids, we can take sum of distances, right? Instead of within cluster sum of squares, we can take sum of distances within that cluster. Okay. But now here we'll have to take sum of all possible pairs. We can't just take from the medoid kind of thing. Okay, we'll have to take sum of all possible pairs, distances between all possible pairs. Okay, so total within cluster sum of squares for k clusters. So you compute for each cluster and then you add all of them together. This is omega k, and omega k star is defined as same quantity, similar quantity, but for data which has been generated from uniform distribution. Okay, so this is similar quantity for uniformly generated data. What do I mean by that? So if suppose I have bivariate data which is say roughly in the bivariate unit rectangle. So suppose all my data is confined to this rectangle, then from this rectangle I can uniformly generate points. So for these points I know that there are no clusters because I have generated them uniformly. So there are no clusters. Now even though I know that there are no clusters, I still carry out cluster analysis on this and get k clusters. Okay, and after getting those k clusters, I compute total within cluster sum of squares for those k clusters. Okay, star is like, it's something like we are testing it as an H0, which says that there are no clusters because everything is uniformly generated. So ideally there are no clusters. So if there are actual inherent clusters present in the data, in that situation, distance between Wk and Wk star should be very high because within cluster sum of squares should be comparatively low if the clusters are natural. Okay, hence the gap statistic is defined as, first you define Gk for k clusters. Gk is defined as mod of log of omega k minus log of omega k star. Okay. Gk is defined as mod of log of omega k minus log of omega k star. We compute this for every k. So 2 clusters, 3 clusters, 4 clusters and so on. And then we take optimal k as that value of k for which this is maximized, because if for that k this is maximized, then it means that clustering with those many groups does make sense, because it is actually drastically reducing the within cluster sum of squares, which is error sum of squares. Okay, so optimal k is defined as argmax over k of gk. Okay, so we have to find that k at which gk is maximized. So argmax, I hope you are aware of this term argmax. Argmax gives you the argument where this quantity is maximized. So we will get value of k for which gk is maximum. Okay. Now one crucial question remains. How do you get wk star? How do you get omega k is fine, but how do you get omega k star? So this omega k star can be obtained via simulations. So you can do say 500 or 1000 simulations, and you can compute gap statistic. So simulations are of course from uniform, and then every time you compute gap statistic and then average over all these simulations gives you final value of omega k star. Okay, so average over these simulations is final value of omega k star. So this is how gap statistic is defined. You might have realized now why the name gap, because it is trying to check gap between these two. In fact, it is plotted via graph also many a times. So what we can do is we can have k on x-axis and gk and gk star on y-axis. So if these are different values of k, then for k equal to 1 you have somewhere here k equal to 2, 3, 4, 5, 6 and so on. So these are suppose from actual data. Okay, and then from uniform suppose things are here. So for k equal to 1 suppose it is somewhere near. Then for k equal to 2 suppose it is here. For k equal to 3 suppose it is here, here, here and so on. So if this is from uniform, then we are trying to see where the gap is maximum. So for example here the gap is maximum, so probably 3 is the optimal number of clusters, hence the name gap statistic. Okay, now we will study another method. So this method is known as silhouette statistics. So what do we do here? Let me denote all ith observation by OI. So OI is say ith observation, and let AI be average distance of OI from the other observation in its own clusters. From the other observations in its own cluster. Okay, so AI is the average distance of OI from other observations in its own cluster. You can compute it very easily, right? Then we compute distance of OI from each cluster also. So we compute distance of OI Cj. What is this? This is average distance of OI from all the elements in jth cluster. From all the elements in jth cluster. Okay, are you getting what we are trying to do here? So we compute distance between OI Cj as average distance of OI from all the elements in jth cluster, and we do this for every cluster. And finally we define Bi as minimum of distance between OI and Cj. This minimum is taken over J, and we have to take minimum only over those J's, means only over those clusters in which ith observation is not there. So OI does not belong to Cj. So Bi is minimum of distances from all the remaining clusters. Okay, and we are taking smallest among them. Okay, so now silhouette statistic for ith observation is defined as Bi minus Ai upon maximum of Ai comma Bi. Okay, Bi minus Ai upon maximum of Ai comma Bi. Now the denominator maximum of Ai comma Bi is just for scaling purpose, so we can ignore it for the time being. So what does Si tell me? If Si is greater than 0, it means Bi is greater than Ai. It means that even if I consider the nearest cluster and its own cluster, so the distance from the nearest cluster is higher than its own cluster. So it would mean that OI is in the right cluster. Okay. So if this is negative, if this quantity is negative, it means that one of the other clusters is closest to OI than its own cluster. In that case, we will have to conclude that AI is in wrong cluster. Okay. So if Si is less than 0, then OI is in wrong cluster, incorrect cluster. Okay. And what happens if it's like, very much inside its own cluster, it's like perfectly sitting inside, then in that case this AI would be very small, the distance from its own cluster would be almost close to 0. So Bi minus Ai would be roughly equal to Bi, and hence Si would be almost equal to 1, because anyway maximum of Ai Bi is Bi in this particular scenario. So if Bi is much higher than Ai, then Si would be approximately equal to 1, and that would mean that ith observation is very correctly and comfortably sitting in its own cluster. Okay, so this is how silhouette statistic is defined for ith observation. Ideally, we finally define silhouette statistic for each cluster and an entire data also. So average over all silhouette indices gives me final silhouette statistic. So S is defined as 1 upon n sum over Si. If most of the values are near 1, then average would also be near 1, and we would consider that clustering as good. So we choose that cluster algorithm which gives highest value of this silhouette index. Okay. So average CI, average silhouette index, should be high for clustering algorithm to be good. Okay. So let me stop here. Thank you.